No, I think you're muted. Still nothing.
Okay, how about that? Can y'all hear me?
Yeah, we can hear you.
Okay, cool. Worrisome. I don't know what happened, but this happened this weekend, so I was prepared. I had a backup sound system, but I don't know why the current one's not working. All right, before we get started, does anybody have any questions?
I was wondering if the chapter 8 stuff was due today. One of them said it was due this morning, and the other one says it's not due for a couple days, so I wasn't sure.
Yeah, I just changed it not 5 minutes ago. I hoped to change it first thing this morning. I think you were the one that had emailed me about it or texted me about it. But I changed it now to Friday of this week, and that should give you plenty of time. We had finished chapter 8, or what I planned on covering for chapter 8. So it's ready to be done. If anybody needs an extension beyond Friday, let me know, because really chapter 9 we're only going to get one day to 1 or 2 days to work on it. So I'm not sure I'm going to be able to finish it in the time allotted. So since I don't have anything, if that's the case, if I don't have any chapter 9 due, I don't mind pushing that chapter 8 back to Sunday, but I think it'd probably be better to get it knocked out beforehand.
Okay, sounds good. When was the final day for the in-person test?
I think I ended up making it Sunday.
Okay.
It did say it right on the actual face-to-face test.
Okay, I just wanted to make sure that that was correct.
Yeah, yeah. I told everybody it's going to be Saturday, but I think I went ahead and made it Sunday just in case.
Okay, cool. Thank you.
You're welcome. Anybody else have any questions? Looks like everybody else has chatted me your first and last name. If you haven't, please go ahead and do that. All right, looks like that's working. All right, so we are starting chapter 9, which is called linear momentum. And I'm going to introduce linear momentum in a few minutes, but it is another vector quantity. So we're going back, which we had done when we were working in energy. We had gotten away from a necessity to work in terms of vectors. You could still come back and get vectors even if you were doing energy methods, but the energy methods allowed you to avoid the actual vectors. It turns out there is a quantity that's actually seemingly conserved in many collisions, or more specifically, it's conserved when the net external force acting on the system is zero. And then you got to realize something we haven't stressed too much is that Newton's second law, the summation of forces is equal to mass times acceleration. There's another form of it we'll be introducing here as well, but basically that law applies to a single body of mass m, but in some sense you can also apply it to a system of bodies of mass m1 plus m2 plus m3 plus m4, so on and so forth, and then that sum counts as the m on the summation of forces equals mass times acceleration. And this new quantity that we're talking about, momentum, is a vector quantity, and it's just the multiplication of mass, which is a scalar quantity, times velocity, which is a vector quantity. And when I show you this new version of Newton's second law, it'll be obvious, or hopefully it should be obvious, why and when momentum is conserved. And that's a key thing to understand. So, for instance, you have some very specific issues you've learned about conservation of energy, and there's very specific cases in which that's applicable. And you should know that. And similarly, there's going to be very specific cases in which momentum or linear momentum is conserved, and you should know that as well. Later, once we start studying rotational motion, we'll also encounter a quantity called angular momentum, and that also has a conservation law. And again, that has a very specific set of conditions under which it's true. So, anybody have any questions on that before we get started? Okay, looks like we're good to go. So I'm going to start off with giving you a definition of momentum, and then I'm going to give you a new version of Newton's second law, specifically because this is more in tune with what Newton actually did write in his Principia. In fact, what we've been using is a specific case that is sometimes applicable. Okay. So first off, I'm going to introduce the concept of momentum, linear momentum specifically. Looks like I got someone coming in now. Okay. So linear momentum is P, which equals M times V. And that is, for a single quantity, it's obvious what that is, but it could also be P total could equal M1 V1 plus M2 V2 plus dot 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 plus M N Vn. So that's what I meant by you can apply F equals ma, for instance, to a system, and your system would have a net momentum M1 V1 plus M2 V2 plus M3 V3 plus dot dot dot. Now, where we get this quantity is from Newton's second law. So let me show you the real version of Newton's second law.
I am not seeing your screen.
Oh yeah, that's not even the computer's fault. That's me completely forgot what I was doing for a second. I'm worried about all that other stuff. Thanks, Jen.
Okay, thank you.
I swear I don't drink before class. I promise. I might do better if I did. Maybe, I don't know. Okay, screen sharing should come on, and this stuff will look a lot more clear now that you actually have what I'm writing down. It'll be very impressive. So what I have is linear momentum, P equals mv, or P total equals m1 v1 plus m2 v2. Notice the vector quantities. Newton's second law, as stated by Newton. Got another person just came in. Okay, as stated by Newton, is actually the summation of the forces is equal to d by dt of mv, which means the summation of the forces is equal to dp over dt. And this, along with these, make up a definition of Newton's second law and a definition of momentum. Okay. Now, remember, the left-hand side is still the summation of all the external forces. We don't count forces like if we had a system like I show up there in P total, I wouldn't count a force on M1 due to M5, for instance, because both of those are part of the system. So when I say the sum of the external forces, what I'm meaning is forces applied to the parts of the system by other things other than other parts of the system. Okay. You can see where if we actually use this version, as I have it drawn right above that arrow, what we get is the summation of the forces is equal to applying the actual product rule for derivatives. We'd get dm over dt times v, and I'll put that in parentheses so no one mistakenly thinks that derivative is still acting on the v, and then m dv dt, which equals dm dt times v plus m times a. So now you can see that, in fact, what we've been using, F equals ma, is really just a special case of this more thorough version of Newton's second law. So let's work on an example. What is a typical momentum magnitude for a tennis ball let's not say hit, let's say served by a top men's men's player. Okay, so what I'm going to list here is that P is equal to MV, which means the magnitude of P, which is just P, is equal to M times V. M is the mass of a tennis ball, and the mass of a tennis ball is around 0.60 or 0.60 kilograms. Yeah, I think that's enough sig figs. And a typical velocity on a serve would be around 61.0 meters per second. Your book has an example like this, and they chose to use, I think, 55 meters per second. 55 meters per second is about 120 miles per hour. Honestly, even Serena and Venus Williams are still hitting at 120, and both of those ladies are retired. So their serves are very well in the area of 120 miles per hour. So I went with a bigger serve. 161's on the order of 140 miles per hour, basically. So that's a more typical elite serve. So let's go ahead and calculate it. What we see is P is equal to 0.062 kilograms times 61.0 meters per second. And here's where you get to see the units, of course, as well. Point zero six 0.062 times 61 is equal to 3.78. And notice the units are kilograms, meters per second. You might even say that's the same thing as a Newton second. Because a Newton, remember 1 Newton is equal to 1 kilogram meter per second squared. So if I actually multiplied the momentum the Newton by a single second, it would give you exactly kilogram meters per second, which is why we use that. So that is the typical unit. We can use Newton seconds or we can use kilogram meters per second. Either one is perfectly acceptable. Anybody have any questions on that? Now, let's say for part B, or let's say another example. Assuming the elite player I'll say players tennis strings are only in contact with the served tennis ball for about, let's say, 3.8 times 10 to the negative third seconds. How large is the force applied by the strings in terms of a 75.0 kilogram person? So what we're going to use here is Newton's second law. It says the summation of the forces is equal to dp dt. We can make this the summation of the forces and treat it all in one dimension is approximately equal to delta p delta t, which means delta p is equal to the net force. I really should draw that a little better. It's equal to the net force times delta t, and this quantity is called the impulse. Okay, now that impulse is an important quantity, but you can see there's two ways of stating it. One way of stating it is it's the change in momentum. It's literally P final minus P initial. Another way of stating it is it's the total force times approximately the time of contact between the thing doing the accelerating and the thing causing the acceleration. Of course, you could also consider integrating it. So we could, in principle, multiply both sides by dt like this. and then integrate both sides. And with that, you would ultimately get delta P is equal to the integral of the total force delta T. So that's another quantity for the impulse. So now you see basically three different ways we could actually specify the impulse. It's the change in momentum, P final minus P initial, or it's the F force times the delta T, or it's the integral of F delta T. So if you made a plot of force versus time, it would be the area under the curve. In our case, what we want to figure out is what is the actual force. So what we're going to say is delta P is equal to mv final minus mv initial. But for a serve, the initial velocity is essentially zero. Yeah, in principle, you could actually throw it up and it'd be slightly going into the court a little bit, but that doesn't give you a marked amount of speed. So we're just going to go with the momentum change being basically the final momentum, which we determined was 3.78 Newton seconds. And that has to be equal to F delta T, where really I'm saying from Newton's second law, it's the summation of all the forces. But in all honesty, the biggest force that this tennis ball is experiencing, at least in a small time interval, is this one hit by the racket, being hit by the racket, specifically the strings on the racket, and therefore all the other forces, if there were any, are very minuscule, so we can just count it as that force. So what I'm going to say is that force is equal to delta P over delta T, which would be 3.78 Newton seconds divided by 3.8 times 10 to the negative third seconds. So you get F is equal to, so I want to divide this by 3.8 times 10 to the negative third. This gives me 995 newtons of force. 75.0 kilograms times 9.80 meters per second every second is 735 newtons. So you can see that this force that elite server would actually put on a tennis ball is markedly larger than the weight of a 75 kilogram person. So you can tell that's a pretty good force. So that's really all I was trying to do is one, get you to see typical orders of magnitude for momentum as well as the units for momentum, and then try to conceptualize this, or at least put it into a context in which you can see how big this force is compared to things like someone's weight. A 75 kilogram person, remember, you're supposed to multiply that by 2.2, so that'd be what, 150 plus 14 pounds plus 15 pounds, so that's what, 165. So it's 165 pounds of a person, and this tennis racket hits it with way more force than that. Anybody have any questions on that one?
So for the formula you use where you have the delta P equals MV final and MV initial, are you saying that that is also equal to the force over the change of time? So like all three of those are equivalent essentially?
No. So what I did was I calculated delta P, which is what I called the impulse. And the reason why was because I know if I divided the impulse by the delta T, that would give me the actual force. So the force is actually given by delta P over delta T on average. Does that make sense?
Yeah, okay.
Okay. All right. So let's look at another example. I'm going to say a person sprays, oops. Good Lord, I'm having a hard time with some English words today. Sprays their car while washing it. In that process, the water leaves the hose at a flow rate of about 1.85 kilograms per second. And I shall say, and the individual let's say clumps of water typically travel at about 22.0 meters per second. What is the force on the car due to the water? We will ignore, or actually I'll say assume the water hits the car and then slides down its side. In other words, we're not picturing the water hitting the side of the car and then bouncing back. We're actually picturing it hitting it and then surface tension sort of holding it on to the actual paint job, so we don't have to worry about any kind of extra force that the car would have to apply to the water to make it come back. So what we can do to look at this is I'm going to write solution, and we're going to make use of the fact that the net force is equal to, on average, delta P over delta T. And I'm going to choose to use it delta P over delta T because I can tell what's going on with this problem. So what I want really is delta P, and you can think of delta P like a dP. So for instance, you'd say dP is equal to G of mv, and that might make you think dm times v plus m times dv or something like that, and that would be fine. But more particularly, if you think about it that way, uh, we're not really so interested in the velocity changing. We're imagining the velocity coming out at a fixed rate, and then it hits the side of the car and then comes to a stop. So looking at it this way, we might realize that dPdt could be written as instead of just a summation of forces, we could say delta P over delta T is equal to delta MV over delta T. And then in this case, you might just say, okay, well, what about delta M over delta T times V? Because that's a real possibility. Now you can say, oh, well, something with the units of mass per time uh, can give me some idea about momentum. So that's what I'm going to do. I'm going to see what the delta MV is like this, because the delta M over delta T is, that's supposed to be about 1.85 kilograms per second. And V is supposed to equal 22.0 meters per second. So I can write 1.85 kilograms per second times 22.0 meters per second. And when I do that, I get 40.7 newtons. Now, what that really is, if you want to think about the momentum a little bit, you can also think about delta P being P final minus P initial. And then you'd have P final is actually going to be 0. And then P initial is M times V, like that. And you say, okay, well, what's happened now is my change in momentum is just mass times velocity. And then I could say, well, the total force is equal to delta P over delta T in one dimension. Now it's not vector wise. So I could say that's actually going to be negative MV over delta T. And then you could break it up again to see yet another way of thinking about it. You could say negative M over delta T times V, and you would get the summation forces is equal to negative, again, 1.85 kilograms per second times 22.0 meters per second. And this, the only difference would give you negative 40.7 newtons. But the answer is really more about the magnitude. So that's two different ways of looking at it. I often use a unit analysis like I did in that first part by recognizing that a quantity like, 1.85 kilograms per second could be represented as a delta M over delta T, and then you just find a way of making use of that delta M over delta T. And because the momentum is actually M times V, and you're ultimately calculating delta P, the P can change because the M changes, or the P can change because the V changes, or the P can change because the M and the V changes. Okay. So in fact, that's what all those other versions of Newton's second law is. You could say M dV dt plus V times dm dt. That's actually where we get the rocket equation, and that's covered in the last section of this chapter, but I will be skipping it. I'll probably be leaving the problems in the actual homework and in the practice tests, though I think I've gotten most of them out of the practice tests. So I don't mind you doing them for homework and stuff like that, but don't focus too much on them. Don't worry too much if you can't get them right, because it really doesn't matter too much. I'm skipping that, and I have no intention of putting that on the test, but it's covered in systems of variable mass, section 910. It really takes some extensive reading to make sense of that, and we just don't have that much time to put into it. What I'd also like to tell you is, remember, I've been going on the idea that everybody knows they should be attempting to read your book in its entirety. There was a section in chapter 8 that you really should make sure you read, and it's specifically section 8-9, potential energy diagrams, stable and unstable equilibrium. I didn't take the time to cover that. I think that's really, really obvious, but there's some terminology in there that you should know. And if you hadn't thought about it, then it might not be obvious. So I definitely want you to read that section. Make sure you understand what we mean by stable equilibrium, unstable equilibrium, neutral equilibrium as well. So, just like with this chapter, you should be reading the whole thing. Even if you just only do it once, you should try to read it in its entirety. Anybody have any questions on that example or anything I just said about chapter 8? Just reminding you. All right. So now that I've given you some examples of how to use momentum, what I'd like to do is talk to you about conservation of momentum. So I'm going to go ahead and break this off like so. Okay. And now I'm going to say conservation. Ah, man. Of linear momentum. So the conservation of linear momentum really starts with Newton's second law. Which says the net external force acting on a system is dp dt. What you'll notice here is if the net external force is equal to 0, I'm going to say red, so if the net external force is 0, then 0 is equal to gp dt. And what does that mean when the derivative of something is equal to 0? Anyone? Let me make sure I got my chat on so I can see if you are typing it. Ah, very good, Joseph, Mr. Skidmore. Yes, if a derivative of a quantity is 0, that means the quantity P, which we could say P of T, is equal to a constant. And that's what we mean by conservation of momentum. The momentum before a collision is equal to the momentum after a collision, assuming that the net external force acting on the system is 0. Now, we have a lot of instances where we can still use conservation of momentum, even though the net external force is not 0. For instance, in a typical collision at an intersection, we know for a fact that the gravitational force is pulling down on the cars, normal force is pushing up on the cars. There's a friction force that's actually going into it. Now, the normal force and the weight, they could actually cancel each other out, and that would mean the net external force could be 0. But to be honest with you, as you actually start to crash, there's a high probability that one of you, if not both of the vehicles, will be skidding, and skidding obviously is friction. That is definitely a force. Now, that being said, it's probably a much smaller force than the force that one car is applying to the other car. So you can probably pretty much ignore that, but realize that you are ignoring it and therefore you have error. Okay. But other than that, we basically say in the event that the net external force acting on a system is 0, then momentum is conserved. And what you would do to write that is you say P initial is equal to P final. And that's a vector quantity. It could mean something like M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final, like that. That's what we mean, both in terms of conservation of momentum, but also in terms of it being a system. In that case, it was a system of two particles, and therefore you can have M1 V1 initial and M2 V2 initial, and those two added together makes the total momentum of the system before the collision, say, and then after the collision, M1 V1 final would be the momentum of one of them, and M2 V2 final would be the momentum of the other one, but the system would have a net momentum M1 V1 final plus M2 V2 final, like that. That is the definition of conservation of momentum. Okay. So in a lot of collisions, we can write it that way. In fact, you're going to see that we usually use the notation. If you imagine for a second that we had a particle A moving to the, darn it. Dang it, there it goes again. If we had a particle A moving to the right with a momentum MAVA like this, and we had another particle B moving to the left with MBVB like that, then in between, we're going to have a collision. And then after the fact, we're going to have something along the lines of this particle A now moving with a momentum MAVA prime. Notice the prime is what we use in lieu of the subscript F. And then B is going to move off with a momentum MBVB prime like that. So that you would get MAVA plus MBVB is equal to MAVA prime plus MBVB prime, and that would be your conservation of momentum equation. Any questions on that? Now that's just for two particles. And of course, that's potentially a two or three-dimensional problem, but it could also be a one-dimensional problem. Once you reduce it to one dimension, then remember the vectorness of it is just treated by calling one direction positive and the other direction negative. So that's how that works. One thing I want to tell you about this, though, is when we start solving these equations for angular momentum, or excuse me, for conservation of momentum, there's a very specific way that your author solves these systems of equations. And in this case, and I didn't realize this when I was you either. So when I was taking the same course, I thought the author was showing us a way that worked in this particular instance. And then I just looked every time for an entirely different way without taking it to heart that I should maybe consider memorizing this way. Completely wrong. Okay. So what I want you to do is when you're paying attention to this, to me solving these equations, when we do conservation of momentum problems, I want you to notice exactly the way the book does its derivations and solves its equations, because that is very specifically the most efficient method to solve the equations that we have. So keep that in mind. When the net external force on a system of objects is zero, the total momentum of the system remains constant. That's what we mean by conservation of momentum. The total momentum of an isolated system of objects remains constant. That's another version of it. Let's look at an example, a really simple example to make sense of it. So what I'm going to imagine is I have a train car A, and it's actually moving with initial velocity v sub a. Notice this is going to, since it's a train, it's going to be on a track, and therefore it's more or less one-dimensional motion. So I'm going to say VA is equal to 10.0 meters per second. And I'm going to say that it's going to run into another train car, B, and VB is equal to 0. So it's basically at rest, right? And then after they collide, they stick together. So if two train cars M equals 10,000 kilograms collide and stick together, what will be their common final speed? Okay, so this is a pretty straightforward one. We have a conservation of momentum system. The net external force is, of course, equal to 0. There obviously is a huge force of A applied to B and then of B applied to A, but they're internal, so that's not a problem. There's obviously a force of a normal force holding them up. That should be counteracted by the actual weight. And their friction force, yeah, their friction force should be fairly minor compared, especially compared to the large forces that one train car makes on another. And that's specifically because that's why trains are designed the way they are, with steel tires, steel rim, steel rails, and steel wheels. They are sort of minimizing the friction as much as they can. So what we're going to do is we're going to say MA VA plus MB VB is equal to MA plus MB. Now that they're stuck together, I can treat them as one thing whose mass is MA plus MB, and the velocity is going to be I'll just say VAB prime, like that. It's all one dimensional. I don't need any vector symbols, anything, that kind of stuff. So now I can put in the numbers. I can say 10,000 kilograms times 10.0 meters per second. I'll say this has 3 sig figs, so I'm pretending, for instance, that only those last 2 digits are not significant figures. Plus 0, that's equal to 20,000 kilograms times VAB prime. So we can get that VAB prime is actually equal to 10,000 kilograms times 10.0 meters per second divided by 20,000 kilograms, again leaving off those last 2, and what you can see is the net velocity will be 5.00 meters per second. Any questions on that? Now, if they happen to not have the same weights, like, one was 10,000 and the other was, say, 9,000, then it wouldn't be exactly cut in half, the initial velocity. It would be something different with it. The main thing is when they stick together, that's what's going to happen. Another thing, when 2 objects collide, that's called a completely inelastic collision. So when 2 or more objects, I don't know if I should say that more because I've never really encountered more than two objects running into each other uh, at the same time to solve as a problem. So I'll put that in parentheses and I'll put a question mark over because I'm not really sure. And I don't know, I don't think I've ever seen anything about it. So I'll just leave that off. When two objects collide, oops. And this is the big part, stick together. The collision is called totally inelastic. Okay. Now that doesn't make too much sense right now, but that's because you don't know what elastic means. Now this part I do know, when two or more objects collide elastically, the collision is conserving, oops, there I go again. Is conserving kinetic energy. So that's the definition of an elastic collision, is when two objects collide or more objects collide and total kinetic energy is conserved, then it's called an elastic collision. Now, if you look back at the other one, the one that was called a completely inelastic collision, that's one in which they stick together. If you looked at that in what we call the center of mass frame, and basically the center of mass frame is the frame in which the total momentum before the collision is zero. So for instance, in this train car example, we might imagine moving to a frame that's moving to the right at 5 meters per second. If we were doing that, then what we would see is the train car A is moving to the right at 5 meters per second, and the train car B is moving to the left at 10 meters per second. Therefore, the total momentum before the collision would be 10,000 kilograms times positive 5 meters per second plus 10,000 kilograms times negative 5 meters per second, which equals zero. And after the collision, if they stuck together, since the total momentum beforehand was zero, the total momentum afterwards would have to be zero as well if momentum's conserved. So they'd literally lose all of their kinetic energy. So that's why they call it a totally inelastic collision, because all of their kinetic energy is lost in such a collision in the center of mass frame. In the center of mass frame, the momentum of the system is zero before the collision and after the collision if momentum is conserved the two objects are stuck together and not moving. Therefore, their kinetic energy was completely destroyed. That's why we call it a totally inelastic. You should know what happened there. Okay, I don't know what's going on here, but something crazy is going on right now with my stupid pointer thing. And it's making it just do this. Let's see if I can find a delete. Nope, that didn't work. That didn't work. I don't have an escape. I don't have that. Let's get rid of that. Okay, so I'm just gonna move it out of the way. There I go again. Jesus. I don't know how to stop whatever's going on here, but it's happening. It's evidently doing writing to text, and I don't know why, and I don't know how to get it to stop. Urgh. Anybody have any ideas? No? Everybody all out of ideas? Okay. So let me try to write it down here again. There it goes again. Darn it. I don't know how. Anybody have any ideas how to get this off? It's really aggravating me. Uh, okay, maybe that did it. Hopefully. Nope, that did not. It just did me the same thing. Urgh. Why is it doing this? I don't see anything there. Does anybody use GoodNotes? Any of you folks? Okay, let's take another poke at it. Okay, it looks like it's working now, so okay, so that's the final statement of that. Does anybody have any questions about totally inelastic collisions and stuff of that sort? All right, you'll look in our module for this week and you'll see I have, for instance, the recoil of an AR-15 and stuff like that. So there's all sorts of different problems you can calculate, but that, for instance, this conservation of momentum is a physical principle that you do experience in everyday life. For instance, if you've ever shot a shotgun or a big gun and felt it kick back on you, what's happening there is momentum is being conserved. So if you imagine having a rifle and or machine gun or AR-15 or whatever you want, right? A cannon, a 50 caliber gun, 100 16 centimeter gun, whatever. any of those sort of things, what you have is a gun with a bullet or a shell or a projectile sitting inside of it, and the gun itself is sitting still as well. So the total momentum before you actually fire the gun or artillery device or whatever, the total momentum is zero. Now, the instant you pull the trigger, basically there's going to be some kind of explosion that's going to cause the bullet or the projectile to take off. And it originally the total momentum was zero, so conservation of momentum dictates that the total momentum should be zero afterwards as well, because the net external force acting on the system really is, in this case, negligible compared to the forces that you're dealing with. So when that is the case, then what you get is a very small mass projectile compared to the mass of the gun, and hopefully to the mass of the person if it's just a a handheld type gun. But if it's like a deck mounted gun on a ship or something, then yeah, the bullets the projectiles can be quite heavy compared to a human. But in this case, let's just imagine a person holding it. What's going to happen is the bullet, which has a relatively small mass, is going to take off with a relatively high velocity, and therefore it has a momentum given by little m because it's a small mass times capital V because it's a high velocity, and that has to be added to the momentum of the actual gun and should give you zero. So that means lowercase m capital V minus capital M, because it's going to be a big mass gun, lowercase v, is equal to zero. So that is actually the recoil equation. That's what gives you how fast the actual artillery device should travel backwards. If that happens to be a shotgun, then you're going to see a shotgun push against your shoulder, and if you're not holding it firmly, it could actually bruise you. Or if you watch any of the crazy videos online, you can see where people have unwisely, like, sort of looked down the barrel with the butt of the gun right in front of their face. I do not recommend you do that. That is not a smart move. And sure enough, the butt of the gun comes back and hits them in their face, knocks them down the hill, all sorts of crazy stuff like that. So keep that in mind. But as an example, you can look at those examples on my YouTube channel. I've got several of them listed in this week's module, but I'm going to do another example right now as well. So here's an example, and what we're going to do is say calculate the recoil velocity of a 7.50 kilogram rifle that shoots a 0.050, God darn it, kilogram shell at 700 meters per second. Okay. So here's our solution. Basically what we have is P initial is equal to 0. It's one dimensional. So that means the mass of the rifle times the velocity of the rifle plus the mass of the shell times the velocity of the shell is equal to 0, but that's also equal to the mass of the rifle times the final velocity of the rifle plus the mass of the shell times the final velocity of the shell, like that. So we can write 0 is equal to 7.50 kilograms times V rifle prime plus 0.050 kilograms times 700.0 meters per second gives me that V rifle prime. This is the recoil velocity, by the way, is 0.05 times 700 is equal to 35.0 Newton seconds. And then that's going to be divided by 7.50 kilograms. And that gives me 4.67. Oh, I've written that way too small. I'll write it down here. Actually, that one's okay. I'm going to say 4.667 meters per second. And it should be in the opposite direction, so I'll put a negative there as well. This should have been negative right there. And this is the recoil velocity. So that's a word that you'll hear over and over again, but now I've sort of stated what it is. Hopefully you'll recognize it. Anybody have any questions on that one? Great. Now my mouse just stopped working. I think it's because maybe my battery just died in my mouse pad. I'm not sure. It looks like it did. Yep, that must be what happened. So now I've got to find my charger. Hold on a second, everybody. I'm working on it. Ah, there's one. So I'm going to put this right here. Hopefully y'all are still here. Got that. And now I'm going to plug this into the back over here. Yeah, there you go. Whew, that was scary. So, no questions on the recoil velocity stuff? Okay. So, your book talks about collisions and impulse. We've sort of done that a little bit. I'll let you deal with the estimating of the karate blow and neat little problems like that. That's not that big a deal. I wanted to go on to the more pressing stuff, which is conservation of energy and momentum in collisions. So we might imagine that another level of physics problem would be not only conservation of momentum playing a role in a collision, but there might also be, like I said, an elastic aspect of the collision. So if the collision is actually elastic, then we have several things available to us. So let's imagine for a second that we have a particle A, and let's say it's moving with a velocity v sub A in the x direction. So I'm assuming all this is one dimensional. And then we have another particle of particle B, say, and let's say it's moving with a horizontal velocity the opposite direction. And I'm going to call that velocity VB. Okay, it's only thick because I tried to make it level and it drew it a little crooked, and then I tried to make it more straight by making it thicker, and it just became ugly. I'm going to say this object has a mass A, this object has a mass B. So in reality, if this is an elastic collision, if this collision is elastic and the net external force is 0, then we have 1/2 m sub a v sub a squared plus 1/2 m sub b v sub b squared is equal to 1/2 m sub a v sub a prime squared plus 1/2 m sub b v sub b prime squared. And we have MA VA plus MB VB is equal to MA VA prime plus MB VB prime, like that. So this is conservation of kinetic energy, and this is conservation of momentum. And we call that equation 2, for instance. So if this is really the type of collision we're dealing with, then we have these two equations, and therefore, in principle, we could have two unknowns. So now what I'm going to do is show you a way to solve the system. And not only that, we're going to get a result that you can just sort of commit to memory. You'll see why it's really easy to commit to memory. But the main thing is we're going to use that, and this method of solving is going to be the way that we do it every time. So I'm going to start off, for instance, with equation 2. So we're imagining an actual solution. So, darn it. So equation 2 is going to give us, what I'm going to do is get all the stuff with the A's on one side. So what I'll do is subtract MA from both sides. And then I'll subtract MB VB. Notice I'm putting all the A's on the left and I'm putting all the B's on the right. Okay, so when I do that, what I get is MA times VA minus VA prime is equal to MB times, this time it'll be VB prime minus VB. Okay, so that's something right now, but it's not really what we're trying to do. That being said, I can also use equation 1 and sort of do the same thing. I'm going to multiply through by 2. And then I'm going to subtract MAVA prime squared from both sides. And then I'm going to subtract MB VB squared from both sides, like that. And what that's going to give me is MA times VA squared minus VA prime squared is equal to MB times VB prime squared minus VB squared. Somebody just tried to come in. So now I have two equations, and they look pretty good, but I could really make it even better by transforming this VA squared minus VA prime squared. We're going to write it now as MA VA minus VA prime times VA plus VA prime. And this side I'm going to write as MB times VB prime plus VB times, oh, that was supposed to be a minus. That's okay, I'll do the next one. VB prime minus VB, like that. Okay. So let's call this equation 3, and let's call this equation 4. And now if I divide 4 by 3, I get this really, really nice expression. The MAs cancel out, and all I get is VA plus VA prime is equal to VB prime plus VB. And that's really what we're going for. This is one little equation that can make life nice and neat. So, for instance, what I can do is I can say that VA minus VB is equal to VB prime minus VA prime, like that. And we could get them in the same order by putting a minus in front of it. If I do that, I can now say VA minus VB is equal to negative VA. Actually, I don't like the way I'm writing that already. It's equal to negative VA prime minus VB prime. So you can see that if you keep the same orders, really the difference just changes. And this is very important, and it's only valid for head-on 1D elastic collisions. So that means you can still use what we call equation 1 and equation 2 up there, but you now have this wonderful equation here that you can use as well. I will go on and show you more of that next time, but it's basically not enough time for us to do another example. So I'm going to go ahead and call it a day. I think you've all already chatted me your first and last name. If you haven't, go ahead and do it again, do it now. But other than that, you guys are free to go, and good luck on your test this week. Don't forget to get it knocked out. There's an online test as well as a face-to-face test. The online test, I think I've given you till Sunday as well. So you should have plenty of time to get that done. And I think I've given you till Sunday to do the face-to-face test. I know I've been in communication with 3 people's proctors. So hopefully y'all can get it done. Thanks for coming, everybody. Have a good evening. And go ahead and register to vote and vote if you haven't already registered, that is. But do vote. Don't get in the habit of not voting.
Thank you. Have a good day.
You too. See you, Jim.
Have a good night, Professor.
You too, Joseph. Have a good one.
Hi, Professor.
Hey, Mark, what's going on, bud?
I'm just having problem with the conceptual questions on Pearson.
Okay. Would you want to pull one out that you're having issues with?
Yeah, it's like 5 questions in total. Is that okay with you?
Yeah, I think I have enough time.
Okay, I'm gonna share my screen now.
Okay.
Oh, I can't share.
Okay, try it now. I just hit multiple participants can share.
So for this one, I'm not sure why it's asking for R2 because like the loop is going this way and I2 is going with the loop and I3 is going against it. So that would be positive I3 and negative I2. Voltage B isn't part of this loop, so I didn't include that. So I'm not sure what I'm supposed to be doing here now.
Oh, okay, so let me read that. As part C, apply the loop rule to loop 2. The smaller loop on the right. Sum the voltage changes. Okay, so what you're doing, let's say you start at that dot down there where the 1 is.
Right
Yeah.
here?
So I'm going to go to the right because that's the direction the arrow is telling us to make the loop. So I'm going to go to the right, past the number 2, and then hang that corner. Notice I'm going the opposite direction of I3. So
Mhm.
that means that resistor is going to be a voltage increase of I3 R3. So I3 times R3, not just I3.
Oh, underscore 3.
Okay. And then I get around to the next dot and I start going down that middle leg. This time I'm going the direction of I2. So that one would be minus I2 times
Times
R2.
R2.
Yep. And that should be equal
Oh,
to 0. Yep.
okay, so I am for this one, I think I know, but I'm gonna try it right now.
Okay.
So it's going, so I'm gonna start here. I go this way, then
Okay.
down, so that's negative I underscore 3,
Uh-huh.
R underscore 3.
Yep.
Then I go this way, then I hit this side of the voltage, which is
This negative side.
negative. Wait,
But well, that's
it
the
would be
negative side.
positive.
But
It
yeah,
would be
exactly.
positive V underscore B.
That should be, yeah, there you go. Good job.
V underscore B. And it's going with I1, so that would be negative I underscore 1, R underscore 1.
Exactly.
Okay, so that's
Good job.
why it was asking for R.
Yeah, remember when it's Kirchhoff's loop rule is about voltage, and Ohm's law says I times R gives you the voltage. So that's why it's not just I, it's times R. The other one's Kirchhoff's junction rule, and that's the one where you just get currents like you have up there in part B.
Okay. All right. Oh yeah, for this one,
Mm-hmm.
I feel like I feel like A and B should be the brightest because they are the first one and they are split the voltage between each other. So they
Okay.
should be the brightest. Then C would be the second brightest because it's right below A and B, but it got more brightest than D and E because D and E got split voltage between each other because they're in series. But when I did that, I didn't get the correct answer.
Yeah, all of them look too much alike to me. It says consider a circuit containing 5 identical light bulbs and a ideal battery. Assume the resistance of each light bulb remains constant. Rank the bulbs A through E based on the brightness. Oh, okay. I just saw they actually have a letter by each
Yeah,
light
so
bulb. Okay,
A,
that's what I wasn't seeing. All right, so what you know is let's assume the battery has a voltage V.
uh-huh,
Uh, what we know is VA plus, let's say, VC is equal to V. If you compare VA and VC, those two added should give you the voltage of the battery. Now, the current in A is basically going to be half as big because A and the other guy, they are all 5 identical light bulbs. So A and its mate in that parallel one are going to
A
have
and B,
half the current.
yes.
Not only that, you need to sort of know what the total current is. Go ahead. What were you going to say, Mark?
Oh, I'm just listening to you.
Oh, okay. So if you first took that setup A and you said, okay, I've got 2 resistor or 2 light bulbs that are in parallel. So 1 over the volt, 1 over the resistance of the light bulb is equal to 1 over one resistance plus 1 over the other resistance. In other words, by putting A in parallel with something, the resistance of that just became half of what it was. So R of the pair is half of RA. And then when you do that bottom branch, that's going to be basically a double resistance. I'm looking still in A. So the bottom square parallel set, yeah, that part. So those two resistors in series make a net resistance that is twice as big as the light bulb, and it's in parallel with one. So what you're going to get is 1 over 2R plus 1 over R. And of course, the smallest, at least common denominator there would be 2R. So that'd be 2 over 2R plus 1 over 2R be 3 over 2R. So you're going to get a 2/3 R for that resistance. And you're going to get a half R for the A resistance. So A would be R over 2 plus 2/3 R. So the least common denominator would be 6. So if I multiplied R over 2 by 3 over 3, that'd be 3 over 6R. And then the other one was 2/3. Now I got to multiply it by 2. That'd be 4/6. So 3/6 plus 4/6 be 7/6 would be the total resistance in that circuit A. So V divided by 7/6R is actually the current. And then that's the way you've sort of got to work this out. It's a little too complicated to just do it off the top of my head without
Yeah.
looking at basically what's going to happen to the currents. In all the cases, well, we can look, let me see. If I'm comparing A to B,
Yes.
A and B should have exactly the same brightness. So I agree with you
Yes.
on that one.
Mm-hmm.
D and E should have the same brightness.
Yes, because they're in series.
Uh-huh. And C should have a different brightness, but C has more current than D or E, and it has twice as much voltage. So C should be the largest, I think.
Okay.
And then A and B, and then there you go. I think that's it.
Okay.
Yeah.
So
Sorry, I wasn't completely following the problem until just then, and then I realized, oh, wait a second, they're just asking about the single resistances. Does that make sense, Mark?
it's a bit complicated.
Yeah,
But
it really is. But the way I ultimately looked at it is when I compared E and D, they were just the same resistors, but in two different spots that are equivalent. So I knew they were equivalent. The same thing with A and B, they were equivalent resistors in equivalent spots. So I knew they were the same. And then that C one was just a matter of figuring out, okay, well, it's in parallel, so it's getting a fraction of the current, but it's getting the same voltage as two resistors next to each other get half of. So for instance, E would only have half as much voltage as C, but it'll have probably, since the IR, it would actually have about the same amount. It would have more current, but the C would be better. So yeah. So that's the way I looked at it. It's really at the end of the day, when you're trying to figure out what's the brightest, it's power, and power is current times voltage. Or one version of it is current times voltage. So if you could compare the current going through C times the voltage in C, that would tell you roughly what the power in C is. And then you do the same thing for A and B and D and E.
okay, I think I can understand a bit.
Yeah, it's not trivial. Don't feel bad if you're not getting it immediately.
Okay, okay. And for this one, yes, it was this one. So like I know Q equals CV,
Uh-huh.
but it's asking me to explain it with only delta V, and I'm not sure.
Find the voltage delta V1 across the first capacitor.
And I believe this is delta V1.
Gotcha. Yes.
I'm like I didn't try this yet, but I'm thinking it's one. Oh,
So what we know is the Q's are all going to be the same.
yes, Q is gonna be all the same across
Mhm.
the series circuit, and
And
voltage is gonna be divided amongst each other here.
Right. So Q over C, or excuse me, yeah, Q over C is the voltage. So since the Q's are the same, 2C is going to have a smaller voltage than C, and 3C is going to have a smaller voltage even than 2C. So the largest voltage would actually be the V1. And what's it say? Find the voltage delta V across. Okay. So what they want you to do is find the equivalent capacitance of those three capacitors. They're all in series, but they're capacitors, so capacitors do that weird thing. So what we have is 1 over C plus 1 over 2C plus 1 over 3C adds to give you 1 over C, the equivalent. So 1 over C plus 1 over 2C would be, obviously the least common denominator would be 6. So I'm going to say 6C over 6, or 6 over 6C plus 3 over 6C plus 2 over 6C. So 3 plus 2 plus 6 would be 11. So that's 11 over 6 would be the equivalent capacitance. 6 over 11 would ultimately be it. So the net capacitance should be 6C over 11.
C over 11.
And then when we have that, we can say the delta V is equal to 6C over, or excuse me. Yeah, 6C over 11. Did you get the same thing as me when you did that? Because I was doing it in my head. It's basically 1 over C plus 1 over 2C plus 1 over 3C. I think that comes out to 6C over 11.
Yeah, something like this. Right, hold up. So 1 over 1C plus 1 over 2C plus 1 over 3C. Then they have a common GCF of 6C.
I confirm that. And then
6 plus 6C plus 2 over 6C. 6C, 6. 11 over 6C, yeah.
okay, so what I found now is that the charge should be 6/11 C times delta V. That's the charge that each of the capacitors have. 6C over 11 times delta V. And then the delta V for 1 would be 6C over 11 divided by V is equal to Q over C. So that'd be 6C over 11 divided by 6C over 11 delta V. So that should be 1 over delta V. C equals Q over V. And that gives me Q is equal to CV. And that also gives me V is equal to Q over C. Oh. Okay, so once you found that equivalent capacitance, now what you can do is remember C equals Q over V. So that means Q is CV. So if you take just the plain C,
Yes, C.
and multiply that by excuse me, Q is CV. So if you take the capacitance C and multiply it by the voltage across it, that would give you the charge. But what we want is the voltage across it. And that V is equal to Q over C. So we already worked out that the Q is 6C over 11 times delta V. And then I'm going to divide that by C. So that first one should be 6/11 delta V. Delta V in the top, yeah. Or to the side, either one would be acceptable.
So wait, how did you get that? Because so I know C is equal to 11 over 60.
Yeah, so you found the equivalent capacitance was 6C over 11. Then I had to find out what the charge is, because remember, the delta V for the battery has got to equal or has got to be related to the equivalent capacitance through C equivalent is equal to Q over V. So you can solve for V, or excuse me, solve for Q, and you end up getting 6C over 11 times delta V. Now, if you want to find the voltage
Don't
drop
solve for-
across capacitor 1, then you need to take the charge and divide it by just plain C. So we had 6C over 11 times delta V. I divided that by C, and that just gave me 6 over 11 delta V. Does that make sense, Mark?
I'm having trouble visualizing it. Can
Here you
you?
go. Let me show it to you on my screen. That'll help a little bit.
Mhm.
So I think I know 1, 2, 3. Yeah, I got this.
Alright.
So I'm going to go to this next page.
Oh, there it is.
Okay. So what we had was a battery, delta V,
Yes.
runs into a capacitance C, and then another capacitance 2C, and then another capacitance 3C. And what we're going to say is Q is the total leaving this. Now, what I found was 1 over C equivalent in series is equal to 1 over C plus 1 over 2C,
2C plus 1 over 3C,
right?
which equal to 11 over 6C in total.
Exactly. So you do know that part. So we'll just kill that and just say C equivalent series is equal to 6C over 11. So now we use C equals Q over V to say that Q is equal to CV. So Q that we have right there, the Q that I just drew, that's the total charge leaving the battery. That's going to be equal to 6C over 11 times delta V,
Uh-huh.
because I'm just using C times V. So I get 6C delta V over 11. Now, delta V1 is equal to Q1 over C1. But Q1 is equal to Q2C, and that's equal to Q3C,
3C.
is
Mhm.
just Q. So what I'm going to do is I'm going to take 6C over 11 times delta V. That's going to go in the top, and C1 is just plain C.
Uh-huh.
So that canceled out there and left me with delta V1 being 6 delta V over 11.
Okay. Yeah, I think I get it now. Also, I think I just noticed a mistake I made. I forgot that series is 1 over C equivalent equal. So I forgot to flip it. I had 11 over 6C instead of 6C
Oh, yeah.
over 11.
That would be a definite a mistake that would cause a problem, obviously, but right. So for instance, just to make sure you understand it, if you now do the same thing with 2C, you can see now that that C cancels out with that C, but now I get 3/11 delta V for delta V2, and delta V3 would be 6C over 11 delta V divided by 3C. And of course, that would just be 2 over 11 delta V.
Okay.
So hopefully that helps you I am about out of time. Do you have another quick one or is that it?
Just one, but I didn't get a chance to start in it, so I don't know how tough it is.
Gotcha.
It's this one.
I tell you what, why don't you, you go ahead and share it now?
Yeah, yeah.
Let me look at it real quick to see what happens.
Yes, I didn't get a chance to start in it, and there's a bottom down here as well. Let me. Yeah, here you go. Oh, I forgot to share my screen, didn't I?
Yeah, I'm just waiting for it. I do that all the time. I'm glad to see someone else does it. So this says if I1 over I0 equals 4 over 5, find I2 over I0. Whoa. An ammeter is connected in series to a battery of voltage VB and a resistor of unknown resistance R. An ammeter reads a current I0 next to resistor unknown resistance R is connected in series to the ammeter and the ammeter's reading drops to, oh good lord, that one's quite complicated.
Oh,
I don't think I had the time, but work on it. And if you run into specific questions, obviously you want to make use of your hints. I don't take points off for that. But if you're still having a problem, send me a text message and any kind of pictures you might have of the work you're doing or anything like that. That'll help me. If worse comes to worse, I'll try to schedule a Zoom meeting with you tomorrow.
okay.
Okay.
Yeah, it's fine. I
All right.
got
Have a
a.
good one, Mark.
Have a good day, Professor.
You too. Bye bye.
Bye.